Hi everyone, today we are going to talk about RC transient response. So what we need, we would like to connect this circuit. This is the operational amplifier. I would like to connect this guy, which is leg number 7 to positive 12 and leg number 4 to negative 12. So for doing that, we are going to connect our power supply in that way, this to this, and then I'll take 12 and negative 12. This is what I'm going to do right now, and then I will connect 100 kilo ohm in series with the capacitor C, which is equal to 0.0 microfarad at the beginning, and this feedback by connecting 2 to 6, and I'm feeding by square wave, which is 2 peak to peak. And then I'm seeing the output voltage across this guy. Then I would repeat the same story by connecting another capacitor in parallel with the same value, and I will see also the output. What I need in this lab, I would like to see the time constant value, which is approximately at 63.2 of the step response. If the step response is equal to a specific value, I will multiply it by that amount to see the value of the time constant. So let us start connecting the circuit. But before I start connecting the circuit, this is what I did. I connected this positive to negative, and then I'm taking the output 12 and negative 12, and I adjusted my power supply. So I will connect my power supply here. Like what I told you, this is the operational amplifier that I'm going to use it, and I will start counting 1, 2, 3 up to 8 over there. So I would like to connect like what we are seeing, 7 to 12 and 4 to negative 12. So here 1, 2, 3, 4, 5, 6, 7. This is 7, which is here. So I will connect this guy to 7, which is positive. I will connect it to 7, and I will connect this guy like what he said to 4. So this guy will be connected to 4. This is my operational amplifier connected right now. Then I can connect the resistor to pin number 6. So pin number 6, which is this guy, I will connect this resistor, and in series with that I will connect the capacitor here. So the resistor is connected to pin number 6, and the capacitor is connected in series, and this leg will be connected to the ground. So this leg will be connected to the ground like what we are seeing. And then I will take this guy as my ground, and I will connect it to my circuit like what you are seeing. Then I'm going to use this function generator, which is connected between pin number 3 and the ground. So this guy is pin number 3 and the ground, but before doing that, I have to turn on my power supply. So I will connect pin number 3 to the positive, which is this guy, pin number 3, and the negative will be connected to the ground. Then what else? I would like to take a feedback from 2 to 6. So from 2 to 6, from pin 2 to pin number 6. This is my feedback. So this is my circuit that we are talking about. Then I will adjust my function generator. If you try to see the function generator, this is the amplitude. I would like to adjust it to 2 and peak to peak, and I would like to use a square function. I clicked on square. And then I would like to adjust my frequency to read 50 hertz, so I will write 50 and hertz. Then what else? I would like to measure the output by using the oscilloscope across the capacitor. So I will connect this capacitor in parallel with this resistor. So I will connect it between this guy and this guy. I can connect this terminal here instead to make it more easier. Now, this guy, which is a channel number 2, is reading the output from the capacitor, and this guy, which is a channel number 1, is reading the input from the function generator. So channel number 1 is reading the input from the function generator, and channel number 2 is reading the outputs across the capacitor. Let me turn this on. So I will turn on channel number 1 and the channel number 2. So channel number 1 and 2, it's working, but I turned it on. I have to wait a few seconds till it started working. Yeah. Yeah, this is channel number 1, like what you are seeing here. This is sine wave. This is square wave, which is the input from the function generator. And like what you are seeing, channel number 2, I will turn it on. Channel number 2 is the voltage across the capacitor. Like what you are seeing for a channel number 1, I have 1 volt per division, and the channel number 2, I have 1 volt per division, so peak to peak is equal to 2 volt. What I need right now, I can make it bigger and smaller like what you are seeing. What I need right now, I would like to use cursors because I would like to use y1x to measure the steady state value for the waveform of the capacitor. Then I will use y2. I will move this guy. So delta y is approximately equals to, like what you are seeing, 1.78. I will multiply this value by 63.2 to give me delta y, which is 1.124. So I will move this line to go to 1.24 as a delta y. So I will move this guy. I need 1.120, 1.124. 1.12, approximately 1.1 delta, which is the difference between those, 1.125. Then I will adjust the location of these two lines by using cursors also, x1 and x2. So x1, I can move it anywhere. I will adjust it here. And x2, I will move it to be on the intersection between what? Between this guy and between this x. At that time, this will be the value that I'm looking for, which is delta x is representing the time constant, which is this guy, and the time constant is equal to here, like what you are seeing, the difference between those, it is equal to approximately 1 millisecond. If you try to calculate the time constant for RC, given R and given C, you will find it is equal to 1 millisecond. I can make this guy bigger a little bit. Yeah. Like what you are seeing, this is the intersection between this x at 63.2 of this value and this line, the intersection between this and this. I put my x here to find the difference between this guy and this guy, which is describing approximately the time constant. I can move this guy a little bit here to make it more accurate. To make it more accurate here. Yeah. So approximately equals 1 millisecond, like what you are seeing. 1 millisecond. After that, I'll repeat the same story by connecting this guy in parallel with this guy and see what's going to happen to the time constant. it will be changed for sure. So I will connect it in parallel here. See what happened. This is the waveform. I will try also to move, by using cursors, I will try to move my x2 to be at the intersection between this guy and this curve. I'm expecting the time constant to be doubled because I added the same capacitor. And this is what happens. Delta x is equal to 2, which is the intersection here. If I try to make it bigger, here, this is the curve. So I used this height, which is 1.125, which is 63.2 of the big value. And I found that the time constant for the next case is equal to 2 milliseconds, which is doubled for the first case because what happened, I connected a capacitor in parallel. So the total value of the capacitor will be equal to the summation of both of them. And I know that RC, if I doubled C, then the time constant will be doubled, which is equal to RC. This is what I need for that lab. I was trying to show you that if I change the value of the capacitance, the time constant will be changed, and this is what happened. I doubled the value of the capacitance by connecting another one in parallel, and the time constant is doubled. I'll see you for another lab. Bye for now.